Hello, and welcome to Lesson 3. Today we're going to be talking about perimeter and circumference. So this should be a much shorter lesson than it was yesterday. So let's go ahead and get started. So let's begin by discussing perimeter. The short definition for perimeter is pretty straightforward. The perimeter is equal to the distance around. It's as simple as that. Now, it may sound simple. We'll see that there are some situations where we really do have to think about it a little bit to arrive at a solution, but the concept is very simple. It's just the distance around the shape. So if we have a simple closed shape like this rectangle that we see, and we were asked to find the perimeter, what we're asking for is what is the length of all the lines, all the sides added together? The distance around. If I had to travel around this rectangle, how far would I have to go? This one is very straightforward because we already have all of the units, all of the measurements for the sides of this particular shape. So it's pretty clear to us if we start by taking this side, we know that that length is 3. So we're traveling 3 units. Now, this 3 could represent 3 feet. It could represent 3 yards, 3 miles. It's not given to us in the problem, so we're going to leave it just as 3. In the end, we'll define our answer as X or a certain number of units. All right. So we'll just say that this is 3 units long. And this side of the shape is 8 units long. So we have 3 plus 8. This side is 3. So we add another 3 on. And then this side again is 8. So we add a final 8. And if we take the sum of these 4 sides, we end up with 11 and 11 is 22. So we have 22 units. And this is what I was referring to. We're just going to give our answer a unit, and we don't know what it is, so we just call it units. So it's 22 units long, you might say. That's the distance around this particular shape. Very straightforward. Let's try another one. And actually, why don't you go ahead and pause the video, see if you can figure out the perimeter for this particular polygon. All right, so hopefully that was very easy for you. All we're doing again is just measuring the distance around. If we start, pick your side, it doesn't matter. Last time we started on the left side. Let's start on the right side this time. So we have this side, well, that's 3 units long. Then we have this segment, which is 2, and another segment of 2, and another segment of 3, and a segment of 4, and we're back to where we started. So we're ready to add all of this up, and we end up with 14. So we have 14 units as our perimeter. Again, very straightforward. Let's try another one. Take a look at this one and see if you can find the perimeter for me. Once again, we're going to add up all our sides. I'm going to start on the left side this time. So we'll begin here. We have a 2. Tack on the next side. Well, that's a 6. Followed by a 4. And then a 3. Followed by another 6. Followed by an 8, which brings us back to the beginning. So again, if you can add, you can find the answers to these problems. We have 8 and 4 is 12. 12 and 9 is 21. And 21 and 8 is 29. So we have 29 units as our perimeter. Okay? Let's try another one. See if you can arrive at the perimeter for this problem. All right, so you may have discovered that this problem was not as simple as the other problems were, right? Because we have some problems here. We know that the length of this side is 8. So that's clear. We know the length of that side. We also know the length of this side. That's 6. And we know the length of this side over here is also 8. And we know that the bottom length is 16. But if we were to take those numbers, we have an 8, a 6, an 8, and a 16, and add those up, we would not have the perimeter. Why not? Well, because there are sides that we didn't count. We didn't count this side. We didn't count this side, or this side, or this side. So clearly, the sum of these numbers is not the perimeter. It's only part of the perimeter. So they left some sides unmarked for us, unmeasured for us, and they left it up to us to figure out what those measurements would be. So to do that, let's take a look at the problem. This is where you need to kind of work on your analytical skills here and decide the best way to, determine the lengths of these sides. Above all, you cannot guess. I will say that up front. You cannot say, oh, well, if this line is 8, this line here must be less than 8. It's not as long, and I don't know, it's maybe 1 or 2 units less than 8. So I'm just going to guess and say it's a 6, or maybe it's a 5. All right? That is the worst thing to do. You need to have some sort of a rationale for justifying what you think the length of these lines are. Okay, so let's try to figure that out. There's a couple ways that we could approach this. First of all, one thing to note is that all of the angles, all of the corners of this particular shape, all have that little box in it. That indicates that they are all right angles. It's straight up and straight across, as we learned in our last lesson. And that is a good thing to know, because what that means is that maybe I'll change color here. This left line, this left leg, so this left leg right here, all right, because it's straight up and down, and because this bottom is straight across, we're forming a right angle, a big right angle here. I know my lines are a little wavy, but it's a big right angle, right? Which means that this line, this bottom line, is perfectly flat, which means that this line, this leg coming up on the right side, is in fact starting right here at this vertex, and that vertex is perfectly in line with this vertex. Okay? So if I were to kind of, take this leg and move it across the page and set it on top of this leg, it would be starting at the exact same location. They're both starting on this bottom line, and this bottom line is perfectly flat because this is a 90-degree angle. So they're both beginning at the same location. All right? So that's important to note. Now, they've actually told us that this leg is 8 units long, and this leg right here is 8 units long. So that's interesting. They both have the same height. So if you imagine a perfectly flat ground, and you have the exact same height pole on both sides, well, that means where they terminate up at the top here, it'll also be exactly at the same height, you might say. Okay? Now, why is this important? Well, think about it. If that weren't true, if we look at just these yellow lines here, if we weren't told that these are 90-degree angles down here in the bottom corners, what we could end up with is something that looks like this. Maybe we have one leg that kind of goes up like this, then we have the big long bottom, but then maybe this leg over here is actually doing something like this, and maybe it's not easy to see. Maybe it's kind of just slightly bent. Now that would be a problem. Why would that be a problem? Well, it's a problem then because if this line were slightly slanted, the top line would have to be coming downhill slightly. Okay, hopefully that makes sense to you. Kind of erase that corner. So if this line is the same length as the left side, because it's slanted, it's not going to be as tall. Does that make sense? If you have a post and you stick it in the ground, the further you slant that post, the closer the top is to the ground, right? You kind of think of it that way. If I have a post, if it's straight up and down, that's going to be the highest point. But as I work my way down and keep the post the same length, the top becomes closer to the ground. And if that top becomes closer to the ground, and then we're putting a lid on this, well, that means this line is then going to start going downhill as well. All right, it's not going to be flat. It's going to be slightly lower on the side that's slanted. Okay? So bottom line, because these are 90-degree angles here, we can show that the left and right side both end at the same height. So not only are they the same length, but because they're both straight up and down, they end at the same height. Okay, so why is this important? Well, we can carry that thought over to the rest of these. Because this is a right angle and this is a right angle, that means that this line here is not only flat, it's also parallel. This line is parallel with this line. Okay? This line is also at 90 degrees on both sides. So this side here is also parallel with this line. Okay? And then this is coming straight down. And this is coming straight down. Okay? And because this is at a 90-degree angle, and this is at a 90-degree angle, we know that this line then is flat as well, which means that this line is also parallel with this line. Everything is parallel to this bottom line, at least all the horizontal lines. And because these are 90-degree angles, this line is going straight up. This line is going straight up. They're both ending at the exact same height. And they're both starting at the exact same spot, which means that this leg and this leg have to be the same height. Hopefully you followed me through all that. This line and this line are the same. So we know that this is 6. Okay? And the only way we can know that is if all of these angles are 90 degree. Now, most of the figures in the book, when they give you problems like this, most of the shapes are going to have 90 degree angled corners. A lot of times, even in the directions, they'll say, assume all angles are 90 degrees, even if they don't put the little boxes in the corners. And the reason they do that is because that really does make a difference. If they weren't all 90 degrees, this shape could be slightly skewed somehow, and this might be close. These two here might be close to the same height, but they may be a little bit different. But because we have 90-degree corners, they are the same height. All right, so hopefully that kind of makes sense. So that tells us what this side is. And now that I've kind of covered everything in yellow, it's a little bit more difficult now to see the other sides that we haven't measured yet. So we haven't measured this side. I'll try to just go over my yellow with a little bit of red. We haven't measured this side. We haven't measured the top here. And we haven't measured the top here. I think everything else we have a measurement for now that we know that this is a 6. Okay? All right, so now let's take a look at this, the 3 remaining red lines. Those are the 3 that we need to figure out yet. So how could we figure out those? Well, this again is going to go back to the fact that we have all 90-degree angles everywhere. And what I want you to do is imagine taking this red line right here, this one right at the bottom, this bottom line. Take that red line and just move it. Move it up so that it sits right here. Now, do you see how this length from here to here, this line, is the same line as the one at the bottom here? How do I know it's the same line? Because the 90-degree angles, okay? Because this is a perfect box here, the bottom of the box, the one side of the box, is going to be the same length as the top of the box. All right? And why does that help us? Well, let's look at what that does. What it does is it completes basically a solid red line across the top of the shape. So if I move this line up here, I now have a complete red line that starts right here on the corner, and it runs all the way across to the corner over here. And again, because this is all 90 degrees, we can recognize that this line is the same length as what? As the bottom line. It's the same length. It's starting right here and going to here. That's the same length. So all I did was take the 3 remaining sides and just mentally moved that line up so that it created a complete line across the shape, which is in fact the same length as the bottom line. So because the bottom line is 16, we know that the top is 16. Now, we don't know what this is, actually. And we don't know what this is. And we don't know what this is. All we know is that these three added together will give us 16. And that's all we have to worry about. We don't need to know what they are actually. Maybe it's a 10 and a 3 and a 3. That might be a good guess, but that's just a guess. I have no way of knowing. But I do know that all three of them have to add up to 16. All right? So what does this do for us? Well, we now have these three red lines figured out. We know that they have to add up to 16, so we'll put that in our sum. And then we know that this side, which was the other unknown part of the shape, is a 6. So we can add that into our shape as well. And now we have all of our sides covered. And I know my picture is a very sloppy mess right now. You probably can't remember what the shape looked like in the beginning. But hopefully you can. These would then cover all of the sides. So now all we have to do is add these up. All right, so adding these up, we have what? 14 and 8 is 22, is 28, is 34, is 40. If I did that right, 4 and 2 is 6. So we end up with 60 units. That is the perimeter of that very messy shape now. All right, good. So hopefully you kind of have an idea as to how to attack these problems. They're all going to be a little bit different. You have to use your head and try to just navigate your way through it by finding different things like this, where, moving lines around in your head. Making sure, though, that before you start moving lines around in your head, that all of the angles are indeed 90-degree angles. That's very important. All right. All right, so next we're going to talk about circumference. So we started off by just finding perimeters of polygons, which have only line segments. Now let's talk about finding the perimeter of a shape that has a curve. In particular, let's talk about circles. All right? So first, let's discuss some of the terminology when we talk about circles. So the first thing is to recognize what the radius is. And in formal language, the radius is simply the distance from the center of the circle to the outer edge. So if we have a circle over here, and if I find my center, the radius is the distance, the length of the line that extends from the center and goes to the outer edge. Right? That is your radius. It's as simple as that. Whatever that distance is, that is your radius. Now the diameter is something similar. The diameter is the length of the line that starts on the outer edge of the circle, and it goes through the center of the circle, all the way to the other side. All right? That is your diameter. Okay, so what could you say about the diameter in relation to the radius? Well, isn't it clear that the diameter is actually just 2 radii, you might say? If I kind of cut the diameter right in half, right at the center, do you see how that is? It's formed by 2 radii extending out from the circle, right? So diameter is simply twice the radius. Twice the radius. 2 times the radius. That'll always give you your diameter. Okay, so that is just kind of some basic terminology. Now let's talk about circumference. What is circumference? Well, it's just a fancy way of saying the perimeter of a circle. So when you hear the word perimeter, you should really be thinking polygon. Think of the 2 P's. Perimeter, polygon. Okay? Perimeter is always measuring the distance around a polygon, which means the shape has to be made up of line segments, no curves. Now, circumference is like the perimeter of a circle. So think of the circumference that starts with the letter C, so does circle. So when you see circumference, you should be thinking the distance around a circle, not a polygon. Okay? So here we have our circle. The circumference is the distance if we start in one location and then move around that circle. How far have we traveled? So how would we find the circumference of a circle, the distance around a circle? Well, the ancient mathematicians, they were very interested in that problem too. And in particular, they decided that there must be some sort of a relationship between the radius of a circle and its circumference, which kind of makes sense. So their assumption was that if I take a circle and think about the radius of a circle, as that circle gets bigger, the radius is also going to get bigger, right? The distance from the center of the circle to the outer edge is going to get bigger. Or you might even say the diameter is going to get bigger. If I make that circle smaller, the radius and the diameter also get smaller. So there must be some sort of a relationship between these two. And if we could figure out that relationship, we could figure out the circumference of the circle. So after much mathematical work, they discovered that given a circle and given a diameter of that circle, call that D, you could show that the circumference, remember the distance around, I'm going to just call it a C for circumference. The circumference is equal to approximately 3.14 times whatever the diameter was. In other words, there's just over 3 diameters. If I were to take this diameter here and start wrapping it around the circle, say that this is, 1 diameter, and then maybe this is another diameter. It's not a very good diameter. This is maybe another, diameter. And then finally, maybe this is a third diameter. And then they still had a little bit left over right here. So they had 3 diameters and a little bit extra that you could wrap around the circle. That little bit extra is the 0.14. Okay? So knowing the diameter then, you could determine the circumference. It's always approximately 3.14 diameters. Okay? And this 3.14 became so important that they gave it a special name, and they call that the Greek symbol pi. So pi is approximately, I'll use the approximate sign, is approximately 3.14. In fact, pi is an irrational number, so there are actually infinite number of decimal places after this 3. But we round it for just practical use to 3.14. If you're interested, here is pi with 100 placement values. So it's 3.14159265358897, blah, 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 on and on and on. So that's, to 100 decimal places. I'll move it all the way over here. There. That's 100 decimal places right there. So rather than make you use that big, long, nasty number, which is actually just a part of the number, it still goes on for infinity, we only make you use the 3.14, okay, as an approximation. All right, so how can we use this in practical terms? Well, this means that we now have a formula to find the circumference, or the distance around a circle. And the formula goes like this. It is 2 times the pi times the radius. Or, another way to write this would be pi times the diameter. So pi times the diameter, that's essentially what we were just showing here. 3.14 times the diameter. You could also consider the diameter to be 2 radii. So that's where this 2 times the radius comes in. Okay. And by the way, we'll learn this later, but when we have things that are written side by side like this, there's always an invisible multiplication sign between these. So the formula is really 2 times pi times r. And this is pi times diameter. All right, so that is the formula. Write that down. It is important. Now let's go ahead and try to solve an actual problem here. So let's find the circumference of these circles. So here we have a circle with a diameter that's 10 inches. So how could we find the circumference? Well, let's use our formula that we just learned. So the formula was the circumference is equal to, since we have the diameter here, I'm going to use the diameter formula, pi times the diameter. Now, what is the diameter? The diameter is 10. So we could call this, 10 times pi. Now, if you want to, write that out as kind of an approximation, 3.14, which is pi, times the 10 is going to be what? 31.4 units. That would be the distance around this circle. All right, go ahead and try the next one. See if you can find the circumference of this circle. All right, so remembering our formula, here we have the radius. That's what's indicated to us. So we're going to use the radius formula, which was the circumference is equal to 2 times pi times r. So we have 2 times 3.14, and I suppose I should use the multiplication sign that you're used to here. 2 times 3.14 times the radius, which they've told us is 2. So now we just need to multiply this out. 2 times 3.14 is going to be 6.28. And then 6.28 times another 2 is going to be 12.56. And actually, they did give us units here. They gave us inches. So we're going to say it's inches. And I probably should have done that over here as well. This is not units here. This is going to be inches. There we go. All right. So hopefully that makes sense. Finally, let's try to sum it up here by combining some of the things that we've learned. What if we have a shape that looks like this? It's not a polygon. It's not a circle. It's a little bit of both. How would we find the perimeter of this shape? What do you think? If you want to pause the video, try this one on your own, and then we'll look at it together. All right, so how did you do? Let's see if you did it right. Here, what we're going to do is picture this as kind of two different shapes. We're going to picture it as a rectangle and a half of a circle. So the rectangle sits here, right? Here's one side of the rectangle right up to that dotted line. And then here's kind of, whoop, that's not right in the right spot. Here's kind of the other side of that rectangle. And then we have the side at the bottom, and then we have the side on this side. There's our rectangle, and then the remaining portion here is kind of our semicircle. And so we're going to divide this up into two problems. Over here, we'll find the perimeter of the rectangle. All right? But we won't count this side, because this side doesn't matter. That's not of any interest to us, because it's not the outer edge of the shape. We're only looking for the distance around the shape. This is not part of the outside edge. So we don't care about that side of our rectangle, but we do care about the other sides. Notice again, this is a 90-degree corner over here. All right, and this is going to be another 90-degree corner. So therefore, we can say because this side of the rectangle is 10 feet, we know that the bottom is also going to be 10 feet. Now here's where it gets interesting. We need to figure out what the length of this side is. Well, let's think about this semicircle over here. It's telling us that the radius of this semicircle is 2 feet. Now I can draw a radius anywhere in the circle as long as I start from the center and go to the outer edge. So if I start from the center here and go to this outer edge, that is also 2 feet long. If I start here and go to this outer edge, that's still 2 feet long. What if I go from here down? That's still 2 feet long, right? Which is interesting. So this little piece from kind of here to here, this is 2 feet. But then also from the center of the circle going straight up, that's also going to be 2 feet. So that's also 2 feet, which means that this this upper piece, this upper radius, and this lower radius, they make up the right-hand side of our rectangle. And their total length is going to be 2 feet plus 2 feet, which is 4 feet. Right? So this side is 4 feet in length. Because we have 90-degree angles, this side has to be equal to that. So this is also 4 feet. So hopefully you see how I arrived at that 4 feet. That gives us the 3 sides of our rectangle, which is perfect. That's all we need. So far, we know to figure out the perimeter, we have a 10-foot, this top piece. We have a 4-foot on the side, and we have a 10-foot on the bottom. So that's where our sum is up to this point. Now we have to figure out the semicircle. So how do we figure that? So on this side, we'll have the semicircle. All right. Well, we don't have a formula for the semicircle. At least we haven't talked about it. We do have a formula to find the perimeter, the circumference of a full circle. And we said that was the circumference is equal to 2 times the pi times radius, right? Well, a semicircle is exactly half of a circle. So the perimeter of a semicircle is going to be half of a full circle, okay? So if this is the formula for a full circle, we can simply divide this by 2 to cut it in half. Put it as a fraction over 2. Or if you're not used to seeing things like that, just put it this way, divided by 2. Okay? All right. So, and I'm maybe just to get you used to it, I'm going to write it as the fraction over 2. I'm dividing it. That's what the fraction sign means. I'm going to divide it by 2. Okay? So, what happens then? Well, let's plug in our numbers. So, we have 2 times our pi. Now, what's our radius? Do we know our radius? Yes, the radius is 2 feet. So we can multiply that. So it's 2 times pi times another 2, because that's our radius, over or divided by a 2. All right? Now, these 2's, we can reduce these. This 2 can go into itself once, can go into this 2 once. All right? And we're left with 1 times pi, which of course is just going to be pi. And then pi times 2. So we have 3.14, that's pi, times 2 all over 1. And anything over 1, we can just drop the 1. So we have 3.14 times 2. If we multiply that, we have 6.28. So we end up getting 6.28 feet for our semicircle. All right? So we need to add that to our full sum up here. So we have 6.28. All right, now we have all our sides because that semicircle covered this circumference right here. Now we have all of our sides. We just need to add this all up. So we end up with, and if you really want to get technical here, we would annex a bunch of zeros in here, and we'd have 0.28. Add this up, and we get a 30. So we end up with 30.28 feet as our perimeter. Excellent. One last one. Why don't you go ahead and pause the video, try this one, and then we'll do it together. All right, so this is somewhat similar to our last problem. We have a couple of shapes here, and there's a couple different ways that you could approach this. One way is to recognize that we kind of have a rectangle here, and we're going to have to recognize this no matter what we do. So we have a rectangle here, right? And then we have 2 semicircles, both with the same radius, which is kind of interesting. Both with the same radius. So we have this semicircle, and then we have this semicircle. Okay? The rectangle is pretty easy because it is a rectangle. We have the top is 6. Well, then the bottom has to be 6. Whoops. And that's the only 2 sides we even care about, right? Because the other 2 sides of the rectangle aren't part of our outer edge. So we just care about those 2 sides. Pretty easy. Now, as for the semicircles, one thing to recognize, and we could do what we did before, which is we could, find the circumference of a semicircle by dividing it by 2. our formula of dividing our formula by 2, and then doing the same thing over here. Or we can just recognize that because they both have the same radius, they both come from the same sized circle. And since they're both halves of the same sided circle, all we really have here is a circle that's divided into 2. Okay? That's all we really have. That circle might be a little bit big. Something like this. Right? It's a circle that we've divided into 2, and then we've taken one half of that circle, put it on the left-hand side, and we've taken the other half and put it on the other side. All right? And then we have a radius of 2. All right? So, bottom line, if we're trying to find the circumference, we're trying to find this outer edge, and we're trying to find this outer edge. But isn't that the same thing as finding these two outer edges, which is just a full circle, right? So we can therefore just use our formula for a full circle to find the sum of these two curves on the outer edges of our shape. So let's do that. So the circumference is equal to 2 times pi times radius. Our radius we know is 2. So it's 2 times 3.14, that's our pi, times our radius, which is a 2. And we'll just do this together, I guess. 2 times 3.14, you might be able to do that in your head. That's 6.28. I think this is what we had last time, actually. And 6.28 times 2 is equal to 12.56 if you do the math on that. All right, so we end up with 12.56 units. Now this is just the perimeter, the circumference of these curved lines. So we have to take our 12.56 and add that to our 6.00 and our other 6.00. And if we add all of that up, we end up with our 24.56 units. So that is our perimeter. Hopefully you got that. Great. Well, I think we will stop here. Good luck with your seat work, and we will continue with more of these problems in the future. I will see you tomorrow.